polarization of electromagnetic waves. This entire video is true for any frequency electromagnetic wave. We tend to think, because we are so keenly aware of light, the visible light with our eyes, we think of polarization of light, but truly this is true for any electromagnetic wave. And to understand polarization, one must really deeply understand what an electric wave is. So let's do a review of that. So typical generation mechanism for an electric wave can be having an electric charge, and something is making that electric charge move. So I got this Q at some location right here. It has an electric field around it, and then it moves up here and accelerates up to there, and it now has an electric field around there. And then this generating electric charge accelerating has therefore a changing electric field which propagates from it. And so even if the generating mechanism is turned off, this electric field which propagates from it keeps going, and this changing electric field changes the magnetic field, which changes the electric field, and this self-propagating mechanism continues, keeping this electromagnetic wave moving away from this source of its generation. And now an electromagnetic wave has many properties. Among them are, so I have this frequency, this generation, so it maintains that frequency in it, so it has a frequency, and then it has energy, it has momentum, and it's shown right here. The electric field magnitude is changing with time, and the magnetic field magnitude is changing with time. And so let's kind of focus in at any moment of time here. So often we kind of show the whole wave, but that's kind of really misrepresentation. You got to think about at any moment of time. So this wave is at a point in space, and so it has now at this point in space I have an electric field which has directionality and magnitude, and I have a magnetic field at that point in space which has magnitude and direction. And we know that this electric field at that point in time and the magnetic field are perpendicular to each other. And since it's a transverse wave, which means the velocity of this wave is perpendicular to its components, the velocity is also perpendicular to those two. And then at some later point in time, where this wave is a different point right here, I drew it right here, so there's my point. Now has the electric field lower magnitude and pointed downward. Magnetic field is now into the board, also different magnitude. And let's just make the assumption that I'm traveling in one singular media through this point in time. Therefore, the velocity of this electromagnetic wave is going to stay constant. So let's say it's even free space. It's in a vacuum. This would be the speed of light then. But if it was a different media, if there's one constant media this was in, then I'd maintain my velocity. And then another point of time, there's the electric field and the magnetic field. And we know that in addition to these two things, we also know, there's a phasing relationship. There's also a polarization direction of this, which we'll talk about later. As far as velocity goes, we know that velocity for an electric wave, this transverse velocity is determined at any point in time is the ratio of the electric field over the magnetic field. Typically we tend to focus on the times when these are maximum, but it's essentially true for all conditions. And we know that the directionality of this transverse electromagnetic wave is given by the direction of the electric field across the magnetic field, and it's very helpful for us that we would happen to use B as a typical letter for a magnetic field. So I always think of B as a second letter, therefore it's the second term of the cross product. So at any point I could go E cross B, and that's that velocity, or E cross B is that velocity, which is, since I'm assuming for this video that I'm in one media, that'll be constant. The other thing I need to really understand about polarization is how polarization affects the energy which is transmitted relative to that's incoming. And we can think in terms of energy, power, intensity. Typically we're going to talk about intensity, and so we'll kind of understand here what intensity is. So energy is pretty simple. Power is energy per time, typically given in watts. What intensity is the power, so the energy per time, or the power going through a particular area. So here I've kind of drawn this area. So think of the area for this wave demonstration. Let's think of this area being in the YZ plane. So I have these electric waves which are perpendicular to this area. Okay, and that's important to know too, that we're talking about intensity being these waves being perpendicular to the area. And so the intensity, or power per unit area, perpendicular to the direction of travel of this electromagnetic wave, is proportional to the magnitude of the electric field times the magnitude of this magnetic field. So these are the maximum values that they achieve here at the point where they're at their maximums, and since they're both in phase. And so that's and since we know that there's a relationship between velocity and the magnitude of the electric field, the magnitude of the magnetic field, we could substitute in for this, and we see that I'd also be that this intensity is also proportional to the square of the magnitude of the electric field. Or I could also rewrite it and replace electric field in here and see that it's also proportional to the square of the magnitude of the magnetic field. For polarization, typically we're going to focus on this, that intensity, which is power per unit area perpendicular to the direction of travel of the magnetic field, is proportional to the magnitude of the electric field squared. And only one of the few characteristics of electromagnetic waves that aren't related to polarization would be the energy content of a photon in a traveling electromagnetic wave, and that's proportional to the frequency of that wave. So therefore, a wave of high frequency, like a gamma wave, would have higher energy per photon than a lower frequency electromagnetic wave, such as a radio wave. Now consider that I have a view which is along the x-axis. I'm looking toward in the negative direction, and here I am, and I see, and what I'm trying to imagine is what's the magnitude of the electric field that from that point of view one would see. So it would be this electric field is only in the XY plane, so I would just see as this is coming towards me, I know that the magnitude of electric field is you're just be going up and down in that singular plane for that singular electromagnetic wave. Electromagnetic wave generating sources, such as an incandescent light bulb or the sun, in reality they have charges which are oscillating at many different planes. So if I look directly in the line of travel of a wave coming towards me, that was my perspective, what you would see would be there'd be many different, infinite number of planes where these true electric fields would be coming for me. I mean, here's just one wave, but certainly that wave could be rotated, and I would see the electric field at a different orientation when viewed straight into the direction of travel. And from the many planes of this oscillating, unpolarized incoming light, we're going to select one singular electric field direction. And so I've shown that as a lighter color blue, and we'll put it right here. So that's one direction of now an oscillating electric field, and I'll just show the amplitude and put it over here. So there's my singular electric field oscillating, and we'll introduce a new concept called a polarized sheet. And a polarized sheet has a transmission angle, and this transmission, and I'll draw arbitrarily as this, that's my transition angle of this polarized sheet for this example. And the transmission angle is the one which allows only the parallel component of the vectorial content of the electric field single through. So no other electric field directions are allowed to go through it. So here's this arbitrarily chosen electric field. There's my polarization transmission axis. And so what's going to go through it is what's the vectorial component of this. And if I define a theta, which is the angle between a incoming electric field and the polarization axis, we can see that what goes through, what's transmitted through the Polaroid sheet is the original magnitude, which comes in, times the cosine of this theta. And now what's absorbed. So what gets absorbed is the sine component. So what the actual Polaroid sheet is, it has long chains of molecules in this direction that the component here excites them and it absorbs them, and it only lets the part of that's parallel to the transmission angle go through. So here, the magnitude of the transmitted electric field is equal to the magnitude of the incoming electric field singular component wave times the cosine of the angle between the transmission angle and this incoming singular electric field direction. And we know intensity, recall from here, intensity is proportional to the magnitude squared of the electric field. So if I take this and square it, well, first of all, we take this one. So this had the incoming signal. It had an intensity, which is just its magnitude squared. So here was my intensity of my incoming signal, is just that magnitude squared. And intensity, recall, is the power per unit area perpendicular to the direction of travel of the wave. So it's in watts per meter squared. So that's the intensity coming in before it gets to the Polaroid sheet. Now what gets through the Polaroid sheet has this amplitude. So the original amplitude of the incoming times the cosine of this differential angle. So the intensity would be this squared. So this is the intensity of transmitted wave, would be the magnitude of the original squared times the cosine squared of theta. And so therefore I take the ratio of what gets transmitted, the intensity, the power per unit area, which is perpendicular to the direction of travel. So that intensity which gets transmitted is the original intensity times the cosine squared of this differential angle between this incoming electric field and the polarization axis. This equation could then be rewritten as the ratio of the intensity of the wave transmitted through the Polaroid to the intensity of the incoming wave. And we see that ratio is a function of the square of the cosine of theta, where again theta is the angle between the incoming electric field and the Polaroid transmission angle. And so therefore, if the angle is 0, the incoming wave and the Polaroid transmission angle align with each other, that ratio is 1, so 100% of that intensity is passed through the Polaroid. If they're at 90 degrees and perpendicular to each other, then none of the intensity in the electromagnetic wave is transmitted through the Polaroid. If they're 45 degrees to each other, then half of the intensity is transmitted through the Polaroid film. So you can see essentially the smallest the angle theta, the greater percentage of the incoming intensity is transmitted through the Polaroid. What happens when an unpolarized electromagnetic wave approaches a single Polaroid sheet with a singular polarization transmission axis? Well, we know that there's going to be the entire spectrum of thetas ranging from 0 to 90. And they all have equal likelihood in this unpolarized oscillation plane. So essentially, all these conditions of theta exist. And so therefore, if I integrate under this curve, I would get the ratio, the average ratio of the intensity transmitted to the intensity incoming. And you'd see that would be half. So therefore, when unpolarized light with its many planes is filtered by a single Polaroid, the intensity transmitted through the Polaroid is 1/2 the intensity of the incoming electromagnetic wave. To test our understanding of some concepts, we have a problem here. Unpolarized light passes through a Polaroid with a horizontal transmission axis. The light then passes through a second Polaroid with a transmission axis which is 30 degrees from the horizontal. What is the ratio of the transmitted light through both of the Polaroids to the incoming light? And also, what kind of assumptions did you have to make to solve for this? So pause the video now, think about the assumptions, and then when you have the answer, restart. So this is the solution. The unpolarized light has electric fields of all orientations, and that's coming to this first Polaroid, which only has a transmission axis horizontally. So because of that random unpolarized light coming to it, the intensity coming out is half the intensity of this unpolarized light coming in. And the electric field coming through here, the only part that's transmitted of the electric field is the horizontal component. So now that's what's left after the first Polaroid. Now coming to the second Polaroid, this coming in, and it has electric field only horizontally, and what gets transmitted is electric field which is 30 degrees from that, which is in this axis of transmission axis of the second Polaroid. So we just need that component, the vectorial component of the intensity going through there. And so then we'll use this equation right here, because remember the magnitude of the electric field is the cosine of theta, but the intensity is the cosine of theta squared. So the intensity, and so we have intensity 1 coming to it and leaving is intensity 2. So intensity 2 is intensity 1 cosine of theta squared. We're told that this second one has a transmission axis 30 degrees from the horizontal, which is also 30 degrees then from the first, what left the first Polaroid. So there's my 30 degrees. So cosine squared of 30 degrees is 0.75. And if we can substitute back in here the intensity of 1 relative to 0 of the incoming unpolarized light, that's right here. So multiplying those together, I get the intensity coming out. The second Polaroid is 0.375 times intensity of unpolarized light coming in, or 3/8. And again, the only electric field component coming out of the second Polaroid is now 30 degrees from the horizontal. Question number 2. How would you arrange two Polaroid sheets to prevent light from passing through? The answer: have the transmission axis of the second Polaroid sheet be 90 degrees rotated from the first Polaroid sheet's transmission axis. So I'd have unpolarized light coming into it. Here I showed them being verticals for the transmission axis of the sheet. So then what all comes out is plain polarized light. If I have the next one 90 degrees, nothing goes relative to it. There's nothing special about that axis. Could be any relative one, these two being 90 degrees. So here, once again, I got unpolarized light over here. This one comes out plain polarized in the same plane as the transmission axis of the first sheet. Goes to 1, which is 90 degrees from that, no light transmitted. So kind of from the end view, you can kind of see, as long as these are two Polaroid sheets 90 degrees relative to each other, no light gets transmitted through the pair of them.